Hello, I'm back with some more waves practice questions. So we're starting here. When used to describe stationary or standing waves, explain the terms node and antinode. Okay, so a node is where the amplitude, or I suppose you could say the displacement, it doesn't really matter, amplitude or displacement is always zero. Nothing is moving at a node. Whereas for an antinode, the amplitude of the, well, standing wave, stationary wave, whatever you want to call it, that's where it can take its maximum value. So, yep, two simple bits of terminology there that you want to make sure you've got firmly in your mind. Right, part B, figure 5.1 shows a string fixed at one end under tension. Frequency of the mechanical oscillator close to the fixed end is varied until a stationary wave is formed. There we go. They've given us the length of the string. You explain with reference to a progressive wave on the string how a stationary wave is formed. Right, we've been through this quite a few times. So we're going to say that we've got an incident wave is reflected at the fixed ends of the string. The reflected wave and the incident wave superpose. This creates a resultant wave of nodes and antinodes through constructive and destructive interference. So all the things you want to mention on this is you want to have incident wave, saying that that is then reflected. So you can say that the incident wave and the reflected wave superpose. So you want to put that in, or you can say interfere. Either one of those. Then you want to say that you've got a resultant wave with nodes, antinodes. So it's just about getting these key terms in this three-step process, as we've been through quite a few times. On figure 5.1, label one node with the letter N and one antinode with the letter A, right? So nodes are the bit where they're not moving. So there, antinodes are the bits at maximum amplitude. So we could have put the N there, we could have put it over here. Yeah, we've got three places we can put the antinode. Oh, actually, that's the next part of the question. State the number of antinodes on the string. 3. So we got one there, one there, one there. So that's those. Right, the frequency of the oscillator causing the stationary wave is 120 hertz. The length of the string between the fixed end and the pulley is 90 centimeters. Calculate the speed of the progressive wave. Right, well, we can see here that we've got 1.5 wavelengths. So if we start at the clamp end, we got one wave, as in we got back to where we started in terms of the wave motion by the time we got here. Then we got another half. So if we got 1.5 wavelengths in 90 centimeters, then that must mean that we've got 60 centimeters for a wavelength. And we've got the frequency being 120, so the velocity is the frequency times the wavelength. So that's 120 times 0.6. So that is going to be, what's that, 72 meters per second to be now 12 times 6. So that's another bit done. This is all going rather well. The speed v of a progressive wave on a stretched string is given by this formula. K is a constant for that string. W is the tension in the string, which is equal to the weight. All right, so they're bringing in these masses of the mass hanging from the end of the string. In B, the weight of the mass at the other end is 4 newtons. Oscillator continues to vibrate at the same frequency. Would you expect to observe a stationary wave when it's changed to 9 newtons? Right, okay, so they're trying to confuse us by putting in something we haven't seen. But we can work out this constant K. So we know that 72, that's our velocity. If we're saying V is K root W, but they've told us V is 72 when W is 4. That's what they've given us there. So that's going to be K times 4. Oh no, square root of 4, sorry. So K is going to be 36. Now we can put all of this in again and say, right, well, V then, for the 9 Newton case, is going to be 36 times the square root of 9, which is 108. So are we going to get a wavelength that's going to fit into this 90 centimeter gap? If we've got we know that the wavelength is the velocity divided by the frequency. So we can say, well, that is 108 divided by 120, because they haven't changed that at all. So that is going to be, what is that? Oh, well, 12 is going to both of these. We've got 9/10. So a wavelength of 90 centimeters. So yeah, that's great. We can draw that at, well, it's going to be the fundamental frequency on this. We're just going to have a straight 90. Oh, no, it's not the fundamental frequency. No. That would be if the wavelength was 180 centimeters. So yeah, the wavelength is 90 centimeters. That's fine. We get one full wavelength inside that distance between the two fixed ends. Yeah, fundamental frequency is if we just had that going on and we just had half of the wavelength. So yeah, it's certainly not fundamental frequency. It's our next harmonic up from that. So yeah, that'd be fine. Yes. You can use this calculation here and say, yes, new wavelength equals 90 centimeters. So that's all good. Yeah, it's a nice question to get us started. What have we got up next? We've got figure 4.1 shows the variation with time t of the displacement y of the air at a point P in front of a loudspeaker with sound waves. Right, to calculate the frequency of oscillation of the air. Right, so well, we've got the period of oscillation. We can see that the period, so the time for one oscillation is 2 milliseconds. So our frequency is going to be 1/2 times 10 to the minus 3. So that's going to be 500 hertz. The wavelength of the wave, which is traveling at that, right? Okay, so wavelength is the velocity divided by the frequency. So they've given us 340 divided by 500, so we can get rid of those and say that is then going to be 68 well, centimeters, wouldn't it be? Yeah, if we've got this, because it's going to be, well, 0.68 meters, so 68 centimeters. Yeah, that's just doubling top and bottom, and then you're dividing by 100, aren't you? So that's easy enough. Draw on figure 4.1 the variation with time of the displacement of the air at a point Q as a distance 1/4 of a wavelength beyond P. Right, so if the wave has propagated on to some point 1/4 of a wavelength later, what will it look like there? Right, okay, so we're going to have to move all of this along 1/4. So we're going to start here, and then we're going to have, well, we're going to have peaks where there are minimum zeros, and we're going to have zeros where there's peaks and troughs. So this is going to be something like this. I'm just marking on the key points because I know when I draw this out it's going to look a right mess. So let's at least try to get it vaguely close. So we're going to go up and down, do it in chunks like that. Okay, this isn't going too badly. And then like, oh, I missed the last one, but you can see where I'm going. I suppose there is that varied time point P in front of the, I suppose we could extend it back. I mean, depending on whether it's just the first propagation of the wave or not, probably doesn't really matter if you include this bit, I wouldn't have thought. But yeah, put it in anyway. Doesn't really make any difference. So we've got to label that Q. So that's Q. Explain the meaning of the term phase difference. Illustrate your answer by stating the phase difference between the displacements of the air at points P and Q. Okay, right, so phase difference. So this relates the oscillations of 2 points on the same wave. And then we can say, and how far out of step. They quite like that term, out of step, in the mark scheme, so I tend to see. One oscillation is from the other. So again, it's that setting up the start of the sentence correctly by saying it's relating the oscillations of 2 points on the same wave. You got that first clause in of your sentence, then it's easy to say that we're talking about one oscillation being out of step with the other. You know, it's much more difficult doing the second part of the sentence if you haven't got that establishing context there. So in this case, they then want us to illustrate an example. So here we can say that there is a pi/2 radians phase difference between these, because that is 1/4 of a wavelength. So 1/4 of 2 pi. So you might even want to put that in as well, 1/4 of 2 pi. Right. The amplitude of vibration of the loudspeaker is increased to produce a wave at the original frequency, but twice the intensity. Sketch on 4.1 the new displacement against time graph for, well, the same amount of time. Well, actually, just the first half of the time, just for one oscillation. Label this curve P. Explain your reasoning. Right, so the reasoning on this is going to be that the intensity is, well, that is proportional to the square of the amplitude. So if we have doubled the intensity, so therefore if intensity times 2, we need the amplitude times √2. That's what we're going to want. So yeah, we just got to draw this again with the same frequency. Change over color on this, but now we want to get multiplied by √2, which is about 1.4. So we're going to want to go up to 2.8 on our amplitudes now. So let's say up here and then down. Again, you know what my eyes are like on these things. Looking at these lines, so we want to go through the higher amplitude, but the same frequency. So we're cutting the x-axis in exactly the same place. We're just boosting up that amplitude. So that's that. I think this has got more question going on, or maybe this is the end. Let's have a look on the next slide. Oh no, we have got more. We've got a part E. So now they've placed an open tube in front of the loudspeaker, such that its far end is at point Q. Right, so this is the same setup. So in the previous part, they gave us the graph for P. We drew the graph for Q in comparison to that. They've now stuck this tube around it all to see if they can set up a standing wave. We've still got that quarter of a wavelength difference between the two of them. Explain how and under what conditions a stationary sound wave is formed in the tube. Okay, so we got two bits to this. We got how and under what conditions. So the how bit we're very familiar with. I'm not going to write it all out again. That's saying the incident wave is reflected from the end of the tube, and the reflected wave and the incident wave superpose and create a standing wave. So that's the how is a standing wave set up bit. So that's the how. But then under what conditions? So we're only going to get a standing wave if the tube is a particular length, because we've got this. Oh, and also, just while I'm before I get onto this, if you have ever wondered why you get a reflection of sound at the end of a tube which is open, how we get a reflection against just an open space at the end of a tube. I mean, I've gone through this in previous videos, but remember, we're getting pressure waves essentially moving down the tube here. So these are going to be bits of high pressure and low pressure. So when a high pressure region leaves the tube, you're going to get a pushing of air outwards as the high pressure part comes out. Then you're going to get the low pressure bit. So the low pressure part appears, and that means you've got lower pressure at the entrance to the tube, at the opening of the tube, than you have everywhere else. So you're going to get a suction effect where you're going to get a force coming from outside the tube, which is then sucking into the end of the tube because you've got that low pressure, and that then rebounds, sets up a wave going in the opposite direction. So that's how you're getting the reflection at the end of a tube, when that low pressure part of the pressure wave that is a sound wave appears. Now, when we're setting up a sound wave, a stationary wave, I should say, in a tube with open ends, so we have to have antinodes at each end. So our fundamental frequency is just going to be that. It's going from antinode to antinode, because remember, antinodes are denoted by having the maximum amplitude. and the nodes are where we're in the middle when we're drawing out these wave profiles. We're drawing what looks more like a transverse wave profile inside the tube because we can't draw the longitudinal ones. So we're looking at the distance from the central axis as being what the amplitude of oscillation is. So in this fundamental frequency here, we've got antinode at each end of the tube. If we're going up to the next harmonic, so that's going to be doing this, where again we've got antinode at each end of the tube. So this has gone from being half a wavelength to 1 wavelength. That's what we've got there. So we're going up in half wavelengths. If we drew the next one, we'd be doing down, up, down. So that's now going through 1.5 wavelengths. So in order to have a stationary wave set up in this tube, we need the tube to be multiples of half wavelengths. So that is what conditions do we need on this. So you want to say at the end that the length of the tube needs to be n lambda over 2 for n equals 1, 2, 3, etc., etc. That's what we need in order for it to work. If you don't have that, then you're not going to get that consistent interference pattern from the reflective wave. We need to have that stable interaction. We need to have that constant phase difference essentially in order to get this standing wave set up. So that is the what, which is very easy to miss. The how we're familiar with, but the what conditions is new in this part of the question compared to the standard sort of stuff you get on these questions. Right, assume that the conditions are met for a stationary wave to be set up on the tube. The distance between P and Q is 1/4 of a wavelength. So 1/4 of a wavelength is always the distance between a antinode or a node and an antinode, whatever way round you want to put it. Describe the motion of the air particles at point Q. So Q is at the opening to the tube. So that must be an antinode because it's at the opening of the tube, which means we've got to describe the motion of the air. So we've got maximum amplitude oscillations in direction of tube length. Direction of tube length. So you want to say, because describing the motion, we need to say, well, how much and in what direction? So it's got maximum amplitude oscillation and it's in the direction of the tube. Because, never forget, although we're drawing these wave profiles that look a bit transverse, everything that's oscillating in the tube is a longitudinal wave. It's going up and down the length of the tube. Point P is 1/4 of a wavelength from Q. So if Q is a node, P must an antinode, then P must be a node. So we're going to get no oscillations, no oscillatory motion. So yeah, there's some nice stuff in that last part of the question, just to clarify some of these things around standing waves in tubes. So right, I think I'm just going to squeeze in one more. It might make it a slightly long video, but I've got one more question on this set of slides. So right, state the principle of superposition of waves. So we want to say that we've got two or more waves meet at a point, and the resultant displacement, that's certainly a key term that you want to get in there. Resultant displacement is the sum of the individual displacements. So the key points on this is you've got to have more than one wave. You need them meeting. You need to talk about a resultant, a sum of the individual ones. So all of those little bits. Coherent red light of wavelength, that is incident normally on a pair of narrow slits, S1, S2. Pattern of bright and dark lines called fringes appears close to point P on a distant screen. Right, so everything they put in this picture. Explain the term coherent. So coherent means we want at least in terms of what they expect for an A-level question, is a constant phase difference between waves. I mean, I say in what they want for an A-level question is because, as you might have seen in one of my other videos, we got differences between temporal and spatial coherence of waves. So is it coherent over time? Is it coherent over space? So I'm not going to go into all of that here, but just be aware there's more than one way of describing the coherence of a wave. And that's something that will come up if you study optics and waves at university. I mean, if you're interested, you can go off and look at my video on coherence. That's done that. Right, so state a value of the path difference between the light waves from slits S1 and S2 to the screen to produce a dark fringe. Right, so we want to get the waves to be anti-phase. So we've got, I mean, they've said it's coherent here. I mean, they haven't actually said that it's coherent and that it's in phase, but let's assume that that's what they're saying. So we need to get, you need to have, for a dark fringe, you need to have half a wavelength multiplied by an odd number, because we need the path difference to be like half a wavelength out of step. So if you multiply this by just 1, our first odd number, then we've got a half a wavelength difference. That means we're going to go, one will be say at a maximum, the other one will be at a minimum. These will then destructively interfere, and you're going to get nothing. So you've got anti-phase going on there, anti-phase interference. Now we can't say, well, let's just have 2 times half a wavelength, because then that's a wavelength path difference. So they'd then be constructively interfering. So we need to have lambda over 2, then say 3 lambda over 2, then 5 lambda over 2, in order to keep getting that destructive interference all the time. So that's why we need it to be an odd number. So odd numbers we can make by doing a 2n plus 1, as in you get an even number, 2n. You can guarantee it's going to be even because you multiplied it by 2. Then you add 1 to an even number, you've got an odd number. So let's do that then. So we need to have the wavelength, so that's 6 times 10 to the minus 7. We need to multiply by 2n plus 1, and we need to divide by 2. So we can change that to a 3. And that is going to be our value of the path difference that we need, because we don't know how many fringes that we've had. It's just saying that it's yeah, we've got a dark fringe. Right, calculate the separation of adjacent dark fringes on the screen near to point P. Use the following data. So this is again from the formula booklet that they give you. The lambda is AX over D. You probably get used to remembering that if you haven't done already. So we want X out of all of this. That is our distance between the fringes. So lambda D over A. They've given us these values. So we've got 6 times 10 to the minus 7. We've got 2.5 for D. That's the distance to the screen. A is the distance between the slits. So it's 1.2 times 10 to the minus 3. So what have we got on all of this? 6 times 2.5 is 15. Let's make that a 12 times 10 to the minus 4. 15 over 12 is 1 1/4. So 1.25 times 10 to the minus 3 meters. So yeah, nice little bit of quick maths there. State and explain the effect, if any, on the position of the bright fringes on the screen when each of the following changes is made. Right, so we only care about position of the fringes here. So the light source is changed from a red to a yellow light source. So that means that our wavelength has gone down. And so if the wavelength has gone down, we can look at this formula here. That means that X is going to decrease. So the fringes will get closer together. That's what we want there. So yeah, you actually write that out. Fringes closer together. Then we got slit S1 is made wider than slit S2, but their centers remain the same distance apart. Right, so we're going to get more light coming in through S1, but it's not changing any of the things that are in this formula. You know, lambda hasn't changed, D hasn't changed, A hasn't changed. So we're going to get no change in position because we only care about position. So no change in position. And then you can say, yeah, because lambda, D and A haven't changed. The viewing screen is moved closer to the slits. So this is similar then to the first one. D has gone down, therefore X has gone down. So the fringes are closer together. Right, it's another really nice question. That was a nice pair of questions on that one, or 3 questions, however many I've done. Really nice set. So, but I'll be back for some more in the next video.